So I want to wrap up with the point by serial correlation. So again, used to measure a relationship between a continuous variable, usually an outcome variable, a DV, and a dichotomous variable, a predictor. So again, methodologically, it really doesn't matter which goes first, but in order to run a point by serial correlation, the outcome does have to be continuous. In other words, we can't have a dichotomous outcome. So generally speaking, we're going to at least conceptualize this as the dichotomous categorical variable at two levels is the IV or predictor, and the continuous variable is the outcome. We're going to use the exact same equation, Pearson's formulation, and in fact, it provides the exact same information as a t-test. So if we ran a t-test and a point by serial correlation, we would find the effect sizes to be similar. We'd get different numbers. The t-test, actual calculated test, would be different than the R, but the p-value would be the same, the size of the effect would be the same. So an example for this is we might compare master's students to bachelor students. So that's the degree completed, and we'd code it as bachelors have a 0, masters have a 1, and we'd look at their semesters at SIUE to see if there is an actual relationship. So again, this would be an example of a point by serial correlation. Now, if we actually had a hypothesis about the difference in semesters at a university compared to the degree completed, we would just run a t-test. The reason we run a point by serial correlation instead of a t-test is as a part of a correlation matrix where we're basically just describing what are the various relationships amongst all our variables in a larger study. And again, to kind of show the relationship between R squared and a t-test, you actually, if you have a t-score, if you calculated the t-score squared divided by the t-score plus the degrees of freedom of the t, you would actually calculate R squared. It's the same thing. So again, these tests mathematically are looking at very similar things. The reason the t-test is going to come out somewhat different is simply that it's not actually converting to z-scores through the process. So the t-test score is still, it isn't on a metric of 1 to -1. It's on a greater sliding scale. So the values are going to be different, but what they're calculating is exactly the same. So the main points. Statistical significance of R indicates whether R differs from 0 and how likely that difference is due to chance rather than due to a systematic relationship between the variables. When interpreting a correlation, we need to first consider, is it significant? If it is significant, we need to look at the direction of the relationship, and we do need to know how the variables were coded when we look at the relationship. We also need to look at the strength of the association and the size of the effect. Statistical significance does not reflect how meaningful the relationship is, simply that it occurred due to chance. So let me talk briefly about needing to know how the variables were coded. So for instance, if you find a negative relationship between two variables, but one of those variables, higher numbers meant more, and the other variable, higher numbers mean less, that actually wouldn't be a negative relationship. The statistics would say it's a negative relationship, but the way the variables were coded actually means that there was a reverse coding on one of your variables. Higher numbers meant less of it. So actually, as one variable went up, so did the other. So again, correlations don't know how you coded your variables. You need to know that as well, and you may actually need to do a little bit of mental adjustment once you've actually run your correlation. What I would suggest is always recode your variables to where the directions make sense, to where if you find a positive relationship, it is a positive relationship. If you find a negative relationship, it is a negative relationship. And a lot of times that can simply be just switching the direction of your variable. So for example, if you had a strongly agree as a 5 and a strongly disagree as a 1 on one scale, and on the other scale it was the reverse, a strongly agree was a 1 and a strongly disagree was a 5, I would just flip the numbers on that strongly disagree scale to where strongly disagree is also 1 and strongly agree is also a 5. So that might just be some recoding, but either way, you need to either do the recoding before you run the correlation, or once you run the correlation, you need to make sure you know how the variables were coded to be able to properly interpret your results. The last thing I want to cover is a little kind of side jaunt, a statistical technique that we can use for inter-rater reliability, and you may run across this in various formats, especially in applied settings. We tend to find it in the medical and clinical fields more than other places, and basically it is inter-rater reliability is an agreement between raters. So we're testing for the similarity between observations of two or more raters, and generally at its simplest level, we're simply looking for the relationship between two predictors or two raters. The actual test is Cohen's kappa, and again, Cohen is pictured there, and his research again kind of mirrors a lot of Gaston's original research. And again, we're going to be looking at it. It basically requires categorical data, and it tests for proportions of agreement. So what this test is for is if you have two raters rating a categorical outcome, for example, need treatment or doesn't need treatment, or maybe three different diagnoses, whether they diagnose someone with one condition, a second condition, or a third condition. And you have data on two different raters looking at the same participants, making the same judgment. Like I said, this is kind of a medical or clinical diagnosis model, but the question is the relationship between their agreement strong enough that you can trust those diagnoses? So the equation for Cohen's kappa is simply the percentage of agreement minus the percentage of chance divided by 1 minus chance. So let's walk through how you actually hand calculate this, and it's fairly quick and easy. But the first thing you need to do is make sure that you actually have the data in the form of percentages. So the P agree is just the total of the percentages that the two raters agreed, and the P chance is the product of every time they disagreed. So let's take a look at how you'd actually calculate this. You'd create a table. So for example, I have two raters, Dr. Doolittle and Dr. Zeus, and they're diagnosing patients with either OCD, ADHD, or neither. So the first thing that I need to do is how often did they agree? How many times, or what was the percentage of times they both said the same patient had OCD? What was the percentage of times they said both students had ADHD? And what was the percentage of time they both agreed that neither? That's my percentage of agreement. I now need to figure out how often they diagnosed in difference with each other. In other words, how often, what was the percentage of times that Dr. Zeus said OCD and Dr. Doolittle said ADHD? In this case, 5% of the time. How many times did Dr. Zeus diagnose OCD and actually Dr. Doolittle said neither, 0.05. So just looking at OCD, the column, you can see that they agreed 15% of the time. They disagreed 10% of the time, 5 and 5. But total, they only actually diagnosed anyone with OCD 25% of the time. So what we're calculating here now is, again, the percentages of agreement. So the percent agree is simply the sum of the pink squares, how many times they agreed. 15%, 20%, and 40%. So 75% of the time total, they were in agreement. P chance is the sum of products of the number of times the sum of the total chance. So how many times did Dr. Zeus predict OCD? 25. How many times did Dr. Doolittle predict OCD? 0.25. We're going to get the sum of products of that yellow square and that green square. 0.25 times 0.25. We're then going to get the sum of products for ADHD and ADHD for Dr. Zeus and Dr. Doolittle. Again, 0.25 is the green box, 0.30 is the yellow box. We're going to multiply those together. And finally, the number of times they both said neither, total, not in agreement, just total that they came up with a neither diagnosis. In this case, 0.45 is the yellow box, 0.5 is the green box. We're going to multiply those numbers together, and then we're going to sum them, add them. So now our P agreement is 0.75, our P chance is 0.3625. And again, those are coming from the pink boxes and the yellow and green boxes. So we're just going to plug those numbers into our equation, Cohen's kappa. So the top of the equation is P agree, 0.75, minus P chance, 0.3625. That gives us the top of our equation of 0.3875. The bottom is 1 minus P chance, so 1 minus 0.3625, which is 0.6375, and then we're going to divide. We come up with 0.6078. So Cohen's kappa for the agreement between these two doctors was 0.61 or 0.6078. The values of Cohen kappa will range between 0, absolutely no agreement, to 1, perfect agreement. And the higher the kappa, the better agreement. Generally, a rule of thumb, 0.75 or better is excellent agreement, 0.4 to 0.75 is decent agreement. There's a pattern there. And that's what we find in this data set. Now again, I just want you to have a general idea of kind of the function of this and the idea of how to calculate it once you have those percentages. There is a couple of videos that I've linked on the Blackboard that actually walk you through a little bit more on how you can do this, including how you can do it in SPSS if you ever actually have to use Cohen's kappa.